June 1st, 2009, Air France Flight 447, an Airbus A330 flying from Rio de Janeiro to Paris, tragically crashed into the Atlantic Ocean, killing all 228 people on board. The flight encountered severe turbulence, and ice formed on the pitot tubes, causing faulty airspeed data. This led to the autopilot disengaging, and the pilots were forced to take manual control. In the chaotic conditions, the first officer, overwhelmed by turbulence, unintentionally pitched the aircraft's nose too high, causing it to exceed the critical angle of attack and trigger a stall warning. The pilot misjudged the situation and made an intermittent stall recovery, lowering nose few degrees below the critical angle of attack, which temporarily silenced the stall warning. But eventually the aircraft entered a full stall, with airflow over the wings disrupted. Descending rapidly at over 7,000 feet per minute, the aircraft's angle of attack steepened, and increasing forces made control more difficult. Despite attempts to recover, the pilots could not handle the loads that built on controls, making it heavier with the increasing speed, and eventually the plane crashed into the ocean at 0214 UTC. The disaster highlighted the crucial importance of understanding the effects of load factor and effective stall recovery procedures. Have you ever wondered why your instructor restricts you from holding larger banks while turning for base at low speed in a circuit pattern? Or why use of rudders discouraged for aligning with the center line in response to an overshooting and approach? Is load factor solely related to bank angle and stall speed? Or why does your aircraft judder during a hard pull in a steep or max rate turn maneuver? The answer to all of this lies in the phenomenon known as load factor. If you're an aviation enthusiast or a pilot, today's topic is a must-know for you. Load factor. We'll explore from its aerodynamic fundamentals to its implications for pilots in everyday flying, and why it's crucial to account for it on every flight. What is load factor? Load factor is simply the ratio of the total lift produced by an aircraft to its weight, expressed as a multiple of gravitational force, or G's. It's a measure of how much stress the aircraft is under. For example, during level flight, when lift is equal to the weight of the aircraft, the load factor is 1 G. But in case of a steep turn, climb, or dive, things change dramatically. Among the effects of load factor to an aircraft in flight, the most significant for a pilot to consider is that it invites accelerated stalls. Aerodynamics of load factor. In straight and level flight, the lift equals the weight of an aircraft. But when you bank the aircraft into a turn, two simultaneous events occur. One, the lift generated by the aircraft is divided into a vertical and a horizontal component, and the lift vector tilts from vertical to oblique position towards the turn. Two, as the aircraft is moving in a circular motion, a centrifugal force is generated which pulls the aircraft out of the bank, referring to Newton's first law of motion, due to inertia of an object to continue in its state of rest or motion until any external force is exerted here. The external force is the centrifugal force. A result of these two events is loss of total lift, thus formation of a resultant vector load in the opposite to the resultant vector of lift. For a level flight, the vertical component must counteract gravity or weight, while the horizontal component works to pull the aircraft into the turn, counteracting the centrifugal force. And in order to maintain level flight, pilot can either 1. Pull the control increasing the angle of attack of the elevator, meaning increase load on control column, or 2. Increase airspeed to increase lift, which will simultaneously increase the effect of centrifugal force, also increasing the load on control column. Not only in bank, load factor is also applicable while pulling out of a dive to level the airplane. In this case, the inertial tendency of an aircraft of going down combines with the weight of the aircraft, requiring more lift to be generated, and load is increased on control column. Even in case of sudden or abrupt climb, a positive load is felt on the control column. In case of abrupt dive or inverted flight, a negative load is felt on control column. Let's discuss loss of lift in case of a bank. The aircraft loses lift, and to counter that, we are increasing the angle of attack. Simultaneously, increasing the angle of attack increases drag, which reduces airspeed. We know aircraft only stalls at angle of attack crossing the critical angle of attack, which is fixed for a particular type of aircraft. In this case, to maintain level flight, we are already increasing the angle of attack, An aircraft is already at low speed, and we don't have much of airspeed to trade, of which means we have already reduced our play before reaching the critical angle of attack, leading to an accelerated stall or increased stall speed. Mathematical calculation of load factor. The redistribution of lift increases the load factor. For example, in a 60-degree banked turn, the load factor doubles to 2g. The wings must produce twice the lift to maintain altitude, doubling the stress on the aircraft's structure and increasing stall speed. Load factor equals 1 by cosine of bank angle. If we consider a 60-degree bank at constant speed and level flight, load factor equals 1 by cosine of 60 equals 2. So the load factor will be plus 2g. And stall speed increases proportional to square root of load factor, vstall directly proportional to square root of load factor. So V equals vstall constant into square root of load factor. For example, if an airplane has a stall speed of 70 knots in level flight, banking at 60 degrees and pilot is trying to maintain level flight, and a load factor is plus 2 Gs, then V equals Vs into the square root of 2 equals 1.4 into stall speed at level flight. So 1.4 into 70 knots equals 98 knots will be the new stalling speed, which is about 40% increase of stalling speed. So the aircraft will stall at the increase the stall speed at 98 knots. Let us simulate an accelerated stall. Consider we are flying straight and level flight at 1.5 kilometers height and 100 knots. We put the throttle to idle and try to maintain level pulling on the controls. Let's see at what speed the aircraft stall. Warning comes at normal condition. It seems 50 knots is in stalling condition. Now let us do the same. 1.5 kilometers and 100 knots. This time we put a 60-degree bank. We pull the control to maintain level flight, building some load on the controls. We can see the stall warning comes at 78 knots. This is why understanding the load factor is vital for maintaining control and avoiding stalls, particularly in high bank angle turns. Common mistakes by pilots. Let us consider a situation. You are in a base turn encircling approach. Your speed is low, closer to stalling speed. You have descended more and made an underturn. Now to maintain level, you pull the control column back, and invertedly, you are applying excessive rudder to steer the nose to align with the center line. You are invariably inviting a conventional spin. A common misconception between steep bank and load factor is that going into a steep turn solely invites accelerated stall, or the load factor, so during initial stage instructor, prevents you from holding larger banks. There is a catch. Load builds up only when you pull on the control column for maintaining level and preventing the descent from loss of lift. If you go into controlled steeper bank understanding the effects in low speed to adjust alignment and let the aircraft descend in a descending turn, there will not be any effect of load factor or accelerated stall. Well, we do not encourage holding steeper banks in base turn. Rather, it is better to remain on the safer side, but you must know to what extent you are capable versus your aircraft limitations and understand what actually happens. During high G maneuvers, pilots exceed the maneuvering speed, especially during the recovery. Let us consider another situation. You entered turbulent weather and inadvertently entered in a steep dive, and speed tends to increase rapidly. Puzzled in the situation, you endeavor to pull out of dive immediately in an uncontrolled manner, building up load on the control column. Even if your wings are level, you are likely to stall the aircraft as pulling the load you have invited accelerated stall speed. Additionally, the angle of attack is high, and there is a considerable amount of chance where you might enter in the region of reverse command, where to maintain lower speed you need more power, which will confuse you further. At higher speeds, extending the maneuver limit can cause structural failure to aircraft. In our subsequent video, we will discuss about the VN diagram and region of reverse command. Managing load factor. Plan for maneuvers and always be aware of load limits when performing steep turns or high-speed descents. Avoid abrupt inputs that could induce dangerous load factors during turbulence or maneuvers. Judge the situation and know your limitation, both aircraft and your personal limitation. Apart from structural damage of aircraft, human factors is a vital point to consider. Pulling excessive load during aerobatics or maneuvers can cause disorientation or even G-induced loss of consciousness, GLOC. Load factor is more than just a theoretical concept. It's a real-world phenomenon that directly affects how you fly and the safety of every flight. Know your aircraft, know your limitations. Thanks for watching. If you found this video helpful, don't forget to like, share, and subscribe for more aviation insights. Fly safe.